Okay. I believe it should be fine now, right?
Yes. Thank you very much.
I'm sorry. Okay, I'll start quickly again. Hi, I'm Hamed. I'm going to briefly explain my recent paper, namely Bootless application of greedy re-ranking algorithms in fair neural T information. As the title suggests, we tried to propose a method for fair neural T information, and it was not successful. So I will walk you through the process. First, we have to start with what is T information. T information is a method to automatically form teams for a specific task or project. In this problem, we have a set of skills, we have a project that requires some skills, and we have a pool or a set of experts, and each of those experts have a set of skills. So our goal is to find a team, or more specifically, a subset of experts that their skills cover the requirements of the project, while their chances of success together is high. And now let's take a look at the real world. On a daily basis, we face some frustrating biases. For example, tech industry is notorious for being male-dominated. In 2022, 58 to 72% of Silicon Valley workforce were male. And since we obtain our data from the real world, these biases will be reflected in our data set, in also our systems. And also T information is no exception. So our analysis on T information baselines without fairness considerations show that these systems are biased based on sensitive attributes, being gender, race, or popularity. In this work, we are going to focus on popularity bias. So to prove this point and other parts of our research, we use the IMDb dataset. In this dataset, movies are the projects, we have genres as the skills, and we have cast and crew as the experts. And also we had to use the filtered version of the dataset because we had to remove the teams with single cast and crew because that was not useful for the T information. And on the right, we have a scene from my favorite TV show, The Sopranos. Most of the cast and crew for this series were not popular by the time that the show started, but they made a masterpiece together. This logic also applies through the other T information problems. If we pick out the best possible candidate for each role in a team, the optimal result is not guaranteed. And this was an example to support that. So how do we define popular or non-popular experts in our dataset? Well, first we have to define our fairness criteria. We stick to demographic disparity. It means that we desire to see the same distribution of popular versus non-popular experts in the dataset and in each of our proposed teams. So we use the average number of teams per expert throughout the whole data set as the threshold to label our experts popular or non-popular. And finally, at the end, we reached the percentage of 43% popular versus 57% non-popular in the data set. And we desire to see that in our output. As we can see in the diagram, our data set suffers the long tail phenomenon, meaning that we got too many experts that participated in just a few teams, and we have few experts that participated in so many teams. And more specifically, we had some cast and crew that participated in many movies, and those are the popular ones. So as our baselines, we used three T information baselines: BNN, BNN embedding, and random. Random is there because it was the best case regarding fairness. Every user or every expert had the same chance of being included in a team or not. And for our re-ranking baselines, we used three deterministic greedy algorithms, namely deterministic greedy, deterministic conservative, and deterministic relaxed. I have to clearly note that these baselines are not our contribution in this research. They are state of the art, and our contribution in this research is putting them together in a pipeline for a fair team formation purpose. So to go over our pipeline quickly, first we have the raw data set. We go over the labeling, and first we have to do the pre-processing and filtering. Then we do the popularity labeling. Then we pass the data to our team formation baseline. And after that, proposed teams will be handed out to the re-ranker, which is a post-processing method. And after that, we run some evaluations, both on utility and also fairness, before and after re-ranking. Utility is also the performance. We use normal IR metrics such as MAP or NDCG. So let's go over an example. Suppose that we want to form a team of 5 individuals for a movie cast. As the slide suggests, blue individuals are popular ones and gray ones are non-popular ones. So if we desire to see 40% non-popular representation, we have to see 2 people from the non-popular group in our top 5. This is the output that the team formation baseline gave us at the moment. So we can see that there's 0% non-popular representation in our top 5. So if we decide to re-rank this team based on deterministic greedy, first we have to create 2 buckets. First, popular bucket and non-popular bucket. And we also put the members inside of those buckets based on the number that the team formation baseline gave us. So the lower score, the lower in ranking means the higher score. And this is an iterative algorithm, and number of iterations is the size of the team. For example, now that we want to have a team of 5 individuals, we have to iterate 5 times. In each iteration, we define a set, and we name it below minimum, for example. And in each iteration, this set contains individuals that their sensitive attribute, that, for example, here is popularity, is below the minimum representation. At the beginning, since we don't have any users or any experts in our re-ranked list, both of our attributes are below minimum. So we have to choose from a below minimum set based on the score. We stick to higher score. So we have to choose individual number 1. Same logic applies again, since both popular and non-popular groups are still below the minimum representation. And also note that below the minimum representation is the floor function of size of the team multiplied by the percentage that we expect to see from that group in our final list. And now at this point, at this iteration, the popular group has reached their minimum representation, which is 60%. Now our below minimum set only contains the non-popular bucket. So if we choose based on their utility or based on their expected performance, we have to choose individual number 6. And now, then again, number 8. If we put these together, we can see that we gained some fairness and we lost some utility or performance based on this score. This suggests that there's always a trade-off between fairness and utility, and we have to consider that through our research. As our fairness measure, we used normalized discounted cumulative KL divergence, or also known as NDKL. KL divergence basically measures the shift between 2 probability distributions. And right here, QL is the distribution of popularity in a team, and P is the desired distribution of a popularity that we desire to see. Now, BNN embedding was our best team formation baseline. And as we can see, although we improved fairness significantly, our utility measures has fallen drastically. We have some potential causes and fixes for this issue. One of the main causes that we have in mind is that these algorithms, re-ranking algorithms, were designed on LinkedIn talent pool. And that's a pretty dense search space. For example, it means that if you change someone in the position number 10 with position number 20, you might have changed someone with the probability 94% with 90%. But in our case, you might have changed someone with the probability of 94% with 60%. And our search space is a bit more sparse. This is one of the causes. And we have some potential fixes. One of them is limiting the scope of our re-ranker. Thank you for your attention. I'll be available for any questions.